Hello, welcome to my part 2 of my lecture 3 on index properties and soil classification of the course Soil Mechanics. So let us first get a quick recapitulation of my previous part 1 of this lecture so that it will be easier as we go ahead in this part 2 of the lecture. So we have already seen or already talked about that soil consists of different size of particles, right? And the different size of particles includes both coarse grained soil particles and fine grained particles. So in order to do particle size analysis, usually a combined analysis, also called as a mechanical analysis, is done. So this is done by two ways. One is the sieve analysis and another is the sedimentation analysis. Sieve analysis is useful for in soil, whereas particles like silt and clay cannot be separated by sieving. So for these type of soil, we prefer sedimentation tests. Usually hydrometer test and pipette test are the common sedimentation test. We have already talked about how the hydrometer particle size distribution in the previous lecture. So in this lecture, what we will do, we will study where we have left the part 2, that about the particle size distribution curve, right? So let's go through it. The result of a grain size analysis performed by a sieve analysis or sedimentation test are usually represented in the form of a graph, that what we call as the grain size distribution curve. Okay, so the grain size distribution curve is usually a semi-logarithmic plot. Like, let me draw this. It has the x-axis or the abscissa as represented as the particle size in, suppose, millimeter, and we have the percent finer in the y-axis. This is y-axis, or the ordinate represents a arithmetic scale, whereas the particle size is represented in a log scale. Okay, so usually this particle size is expressed as a equivalent diameter, which corresponds to the sieve opening size for coarse grained soil, or it is the size of the spherical particles when falling through a soil suspension in a sedimentation test, right? So this particle size distribution curves can be represented like, suppose it's 10, it's 1, it's 0 0.1, 0.01, and suppose this is an arithmetic scale, so it's 0, it's 10, it's 20, it's 30, and so on. So this curve looks like that of an S. Okay, so it's a reverse S drawn, or it may be also drawn like this, the particle size such that it increases from left to right. So suppose this is 0.01, it's 0.1, this is 1, this is 10. So this is the particle size, right? And similarly, the y-axis remains the same. The percent finer represented in an arithmetic scale, and it looks like this, right? So the particle size distribution curve, we can say it's a semi-logarithmic plot with percent finer in the ordinate and size of the soil particles in the abscissa. So now the question comes that why a semi-logarithmic plot, right? So this may
be justified as, since when we are doing a grain size analysis in the soil sample, the range of particles may be from coarse to fine, and there's a large range of size of particles, right? So in order to give a very like range of particles well represented in the graph, this semi-logarithmic logarithmic plot is more suitable, right? So we can write, for better representation of large range of particle size, also we can say that, okay, I'm writing the 2.2 point here, that as the soils, if we compare different soils of equal uniformity exhibit the same shape in the particle size distribution curve irrespective of the actual particle size. So let me write this. Soils of equal uniformity exhibit same shape irrespective of the particle size, right? So what do we mean by equal uniformity? This word will be very clear as we go on to the next slide. Okay.
So before we explain more and go into greater details, let me draw the grain size distribution curve of some soils. Okay, this is my x-axis, which comprise of my percent finer in arithmetic scale, and this is my y-axis. And suppose we mark it in this way when the particle size decreases from left to, so it's 10, suppose this is 1, this is 0.01, this is 0.001. So this is my particle size represented in a log scale. So suppose we represent it in millimeter. So let me draw some particles distribution curve. So suppose this is my soil sample 1, this is my soil sample 2, this is my soil sample 3. So we will say that observing the particle size distribution curve, its position, its shape, its slope, it will give us an indication of the type and the gradation of soil. What do you mean by the gradation of soil? Usually, the distribution of particles of different sizes in a soil mass is called as grading, or that what refers to the gradation of soil. It's a distribution of particles of different sizes. Okay. So, the grading of the soils can be determined from the particle size distribution curve. If we closely observe 3 of the graphs, we can say how the particle size reveals whether a soil is coarse grained or whether grained, and thus tells us about the type of the soil. So if a curve is situated more higher up and towards the right, that is, we see as the particle size is decreasing towards the right, and higher up means that more number of particles will be finer than a particular size considered on the graph. So this would represent a fine grain type of soil, whereas curve which are situated more towards the left, that we can see that the particle size is increasing towards the left, right, as we see the graph. So towards the right, it represent a coarse grain type of soil. Okay, now corresponding to the telling about the gradation of the soil, we can say that we can use different terms. This term will be more justified when we define the terms what we say as the uniformity coefficient or coefficient of curvature. So we see the term, these two are basically shape parameters which are defined for a particle size distribution curve and will tell about the gradation of soil. So Cu is basically, it's equal to D60 by D10. So what do we mean by D60 and D10? So suppose we can draw a clearer graph of one soil only. So suppose this is 10, this is 1, this is 0.01, and this is the particle size in the x-axis in a log scale and percent finer axis, right? So D60 represents a particle size corresponding to which 60% of particles are finer than this, right? So suppose on the graph we plot, so suppose in the y-axis this corresponds to 60% and we take the corresponding point in the y-axis. So the particle size corresponding to this 60% finer will be written as D60. That is D60, 60% of particles are finer, right? Now what is my D30? So see, D30 is the particle size corresponding to 30% finer. So if we draw on the curve, 30% we take in the y-axis and we take the corresponding point on the x-axis. So this is my D30. That is 30% of my particles are finer than this size. Okay, now what do we mean by D10? So D10, similarly, if we take my percent of on the graph, so and we take the corresponding in the x-axis, so this is my D10. So this is my 10%. So D10 represents a size in millimeter, as suppose we are taking the x-axis, the particle size meter, such that 10% of the particles are finer than this size. And here D10 is also called as the effective size or effective diameter. Okay, so the ratio this particle size of D60 and D10 is represented as the uniformity coefficient, We also define another term Cc, which is called as the coefficient of curvature and is represented as D30 square divided by D60 in D10. Okay. So with these sizes, these two quantities are defined. Now, using these two shape parameters, now to back on graph the curve that we have drawn here, the three curves that we have drawn, we can again define three kind of soil as marked by 1, 2, 3. So what are the three types? So if we observe graph 1 or curve 1, we can say that the soil sample is well graded. That means it has a good representation of particles of all size. That is, we see the graph is well spread over the all part of the area under this, representing particle sizes from coarse to fine. So it's a well graded soil. So we can say my soil 1 is well graded. Okay. Next, we will say what is my soil sample 2. We see that my curve 2 is mostly confined to a very narrow area of the curve, of the area under the curve, right? So this we see that it only considers a very small range of particles. Thus we can say the soil represented by 2 here is a poorly graded soil, or we can also say a uniformly graded soil. That is, it has an excess of certain particles or deficiency of certain particles, or it has most of the particles about the same size. And thus when the particles is of the same size, it's called as a uniformly graded soil, and it has more excess or deficiency of certain particles. So we see here graph 2 is mostly confined between a range of particles between 1 and like less than 0.01, right? So this is the range of particles it has been considered. So we can say it's a poorly graded soil. Or uniformly graded. Next, type 3 type of soil as represented in the graph, we see that we observe a very flat portion, right? We see this flat portion of the curve. So this flat portion represents that some of the intermediate size particles are missing. That is, for these range of particles, the percent finer is almost the same. That is, the intermediate size particles are missing, and there is a gap in the gradation, and hence it is called as the gap graded soil or skip graded soil. So this we can say is the gap graded or skip graded soil, right? Now, before what we defined Cc and Cu, using these two shape parameter, we can also say how my when my soil is well graded, or when it can poorly graded, or when it can be gap graded. So let us draw a table for this. Gradation characteristics based on Cu and Cc. So suppose we write this as soil type is my first column. Then we have gradation of soil, my column, and we will assign certain values for Cu and Cc. Okay, so if my soil type is gravel and Cu value is greater than 4 and Cc value is between 1 to 3, we can say my gravel soil is well graded. Okay, so suppose particle size distribution curve, knowing the values of D60 and D10, we can find out Cu, and from Cc also D30 squared by D60 into D10, we get the values greater than 4 and Cc between 1 to 3. We can soil is a well graded gravel sample, right? Now suppose the Cu and the Cc values doesn't come like greater than 4 or between 1 to 3. That is, the above requirements are not met. So what we can say, my soil is a gravel which is poorly graded. Right? We saw what is poorly graded soil in my previous slide. Again, suppose we observe a particle size distribution curve of a soil and we find my Cu value comes greater than 6 and my Cc value comes same between 1 to 3. So we can say my soil type and about the gradation of soil, that is, it's a sand which is well graded. And similarly, if the above requirements are not satisfied, we can say it's a poorly graded sand, right? So these grain size distribution curve, this defining Cu and Cc, are more useful for coarse grain soil than for fine grain soil. For fine grain soil, usually we use Atterberg limits as the more perfect index property in classifying or describing them, which we will see later in other lecture. Okay. So let us solve one given problem, as we can see about finding the grain size distribution curve corresponding to a sieve analysis conducted with 500 gram of dry soil. So we have in my previous lecture we have already got some idea about how to determine the percent finer corresponding to sieve analysis. So here through a problem through the table given below, let us try to make that idea more clear. So we see the table. The IA sieve size is given, and corresponding to the sieve size, what is the weight of the soil retained in that particular sieve is given. So we know our diameter of the particles in the soil sample corresponds to the sieve size opening, right? So we can write what is our diameter of our grain, right? So let us write it. Diameter of grain. We write it in meter. So this will, let me change the color of the pen. Okay, so this is my 4.75, this is my 2, this is my 1. 425 micron corresponds to 0.425 millimeter, then 212 corresponds to 0.212 millimeter, 150 corresponds to 0.150 millimeter, and 75 micron corresponds to 0.075 millimeter. Right, now we find out what is my weight of soil retained. That is, we have already have our weight of soil retained, so we will find what is our cumulative weight retained. So we have the cumulative weight of soil retained. So this is also in gram. So our cumulative weight retained. So let's calculate. So this is my 20 gram as it is. Now the cumulative for the next will be 160 plus 20, then it's 180. Next is 120 plus 160 plus 20, that is 300. Next is 100 plus 120 plus 160 plus 20, that is 400. Next is 65 plus 100 plus 120 160 plus 20, that is 465, and accordingly we calculate the rest. It's 475, and this is my 480. Right, now we have to find out what is my percentage of the soil retained. Percentage of soil retained. So this percentage is calculated on the basis of the total sample of soil taken, that is here it's 500 gram. So how to calculate? So it's basically 20% of cumulative weight soil is retained, and it's divided by the total soil sample taken, it's 500, and therefore into 100, and this gives 4%. Right, similarly what we do, it's 180 divided by the total sample taken into 100, so we will get 36%. Right, so similarly we will calculate the rest. So it corresponds to 60, then it's 80, it's 93, 95, and 96. So all the viewers can try calculating it and find out if I am correct. Okay, so now finally our main requirement is that we need the percent finer to plot the grain size distribution curve. Right, the percent finer will be plotted on the y-axis and the diameter of the grain will be plotted on the x-axis. Right, so let us calculate now our percent finer. So our percent finer is basically what percentage of soil has passed that particular sieve. Right, so when 4% of the soil is retained, that means our 100 minus 4% has passed through that sieve. That is, we can write is 100 minus 4, that is 96% is our percent finer for 4.75 millimeter sieves. Right, similarly 100 minus 36 is equal to 64%, corresponds to percent finer than sieve 2 millimeter. Similarly, we calculate the rest and we get it's 40% now, 27, 5 and 4%. Okay, so now we can plot our grain size distribution curve, and then we will find out what is my percentage of gravel or coarse sand or silt clay fraction from the curve, and accordingly the effective size, and then the gradation of the soil. Now I'll suggest the viewers to get a semi-log graph and try to draw and plot this grain size distribution depending on the values calculated as given on the table in the previous, right? So for me, I'll just try to give an approximate plot as I draw it here. So we draw, this is my y-axis and this is my x-axis, and I am not drawing to scale, you can already see that. So this is my percent finer on the y-axis, and we have the particle size. Let me mark it in millimeter on the y-axis. Okay, so let us draw by representing the particle size decreases from that of the left to right. So it is 10, this is 0. This is 1, this is 0.1, this is 0.001 and so on. So suppose if you plot the graph, the values from the table, it looks like a inverted S. Okay, so let me mark some values on the y-axis too. Suppose this is 10, this is 20, 30, 40, 50, 60, 70, 80, 90, 100. So these are the some values. We can see from the table corresponding to 96% finer. So suppose this is the point, we get a particle size as 4.75 millimeter, right? Corresponding to 2 millimeter, we get 64, so it will lie somewhere here. So it would be 2, right? So let me pass this graph from here. So right, so this is very an approximate one. When we draw to scale on the same graph, it will be more well defined, right? So this is I've just marked here some points is 2 millimeter, right? Now we have to find out what is my percentage gravel as given in the question, right? According to the IS as mentioned, we know that the percent gravel is when the particle size is greater than 4.75 millimeter. That is, from the table we see that my 96% is finer than 4.75 millimeter. That is, what is my particles which is greater than 4.75? Definitely 100 minus 96. So 4% are my gravel fraction. Now we are asked to find what is my percentage of coarse sand, which according to the mentioned the IS code, we have particles ranging from 4.75 to 2 millimeter. Therefore, from the table, we find out my percent finer is corresponding to 4.75 millimeter is 96%, and finer than 2 is 64, Therefore, if we subtract the 2, we will get the percentage retained in between 4.75 to 2 millimeter size, and that what we represent as the coarse sand, and therefore this is equal to 32%. So 32% is my coarse sand fraction. Next, we have been asked to find what is my silt and clay fraction, which will represent the particle size less than 0.05 millimeter. That is, we see from the table that my corresponding to ISC size 75 micron, we will see my percent finer is 4%. That is 4% of particles or 4% of the soil samples has passed through the 0.075 millimeter or 75 micron sieve. That is, the one which has particle size which is passed corresponds to the silt and clay fraction, that is particles less than 0.075 is 4%, as we can see from the table. Now we have been asked to find what is my we have been asked to find what to comment on the gradation of the soil, right? So we have talked in the previous slides that to comment about the soil gradation, we can define two terms. One is Cu, another is my Cc. So if we can get the values of Cu and Cc, we can comment on the type and the gradation of the soil. So what is my Cu? Cu is equal to D60 by D10, right? So what we can do, from the curve on the y-axis we find 60% finer, so we can take the 60 from the y-axis and drop the corresponding perpendicular line to get my x-axis value. So this will represent my D60 millimeter particle size. So from the graph we can read it and we can write it, right? Because I have drawn it in a very approximate scale, I am not sure what the value might come on the x-axis. So corresponding to D60 we will write it here, divided by D10 refers to particle size corresponding to 10% finer. So this is my 10% finer, right? And similarly we take the corresponding x-axis to get my particle size, which we refer to as the D10. So we will also get the value here, and similarly we will write it. Same for Cc, which is D30 square by D60 into D10. So D60 and D10 values already I have said 30 corresponding to 30% finer. So we obtain this 30% and drop the corresponding value on the x-axis to obtain D30 particle size. And similarly we will get some value. We already talked about in the previous table that if Cu is greater than 4 and Cc value is between 1 to 3, we can say it's a well graded gravel. If the above numerical values of Cu or Cc doesn't come, then we will say it's a poorly graded gravel. And if our Cu value comes greater than and Cc same between 1 to 3, we say it's a well graded sand. And if my values of Cu or Cc something else rather than that, we will call it as a poorly graded sand. So similarly here, since I did not draw it on a graph, I'm unable to the value of Cu and Cc, so the viewers must give it a try and they must plot it on a semi-log graph and find out the value of Cu and Cc. So that's all for this lecture. The next lecture we will talk about my index properties, which is more relevant for fine grained soil. That we will talk about the consistency of fine grained soil. We will talk about Atterberg limits. So see you in the next lecture. Thank you.